Okay, welcome back to lecture 8, part 2. Now we are going to talk about proteasome inhibitors. Okay, we said that we are going to talk about all the miscellaneous agents in this lecture. All right, so what are proteasome? The proteasome is a complex structure which can be viewed as the cell's rubbish disposal unit. Okay, it's an ATP-dependent multi-catalytic protease that destroys proteins. Okay, the prime rule is to eliminate damaged or misfolded proteins and to degrade key regulatory proteins. All right, so it's a destruction machine. It's a protein killing machine. Okay, so cells have to save their good proteins from this machine. So what they do, cells mark their defective proteins with a molecular label so that they can be recognized by this protein killing machine. Okay, this molecular label is a protein that is called ubiquitin, and I think you learned about ubiquitin in your previous studies. I think in your last year, if I'm not mistaken. Okay, anyway, so this proteasome destroy proteins. Okay, and we want to destroy cancer cells. So theoretically, we should enhance the actions of proteasome, right? We should activate proteasome. Well, the strategy that was developed is to inhibit those proteasome. Someone will say, well, that's counterintuitive. Well, it is not completely counterintuitive because proteasome, when they destroy those proteins, they clear or clean the cell. Okay, so when you inhibit the proteasome, that will lead to the accumulation of the proteins, and accumulation of the proteins leads to cellular crisis and eventually apoptosis. And that's what we want. We want the cancer cell to die. We want apoptosis, right? So bortezomib is a boronic acid dipeptide, as you can see here. It's a boronic acid dipeptide. This is peptide 1 and this is peptide 2. Okay, it inhibits the proteasome by forming a boron threonine bond at the active site. So this boron here is important. Okay, bortezomib is the first proteasome inhibitor to be approved for the treatment of multiple myeloma. Okay, so this is the first one in the market. Okay, it's a clinically active agent. Bortezomib is not prone to multi-drug resistance or multi-drug resistance, which is something good about bortezomib, Velcade. Okay, it is not prone to resistance. All right, aclarubicin or aclasinomycin A, which is a natural product. It's an anthraquinone due to this, the anthraquinone ring system, and it affects proteasomes by inhibiting the chymotrypsin activity of the structure. As we said, proteasome destroy proteins and it degrade proteins. So basically proteasome has many activities that resembles proteases. Okay, one of them is a chymotrypsin activity. So the aclarubicin or the aclasinomycin A inhibit the chymotrypsin activity of the proteasome. Okay, they found that the tetracyclic moiety, this one, and the 3 sugar ring system, these are all necessary for activity. So if you remove the sugars, you will lose the activity. If you remove the tetracyclic system, you will also lose the activity. All right. Let's move to another subject, which is the histone deacetylase inhibitors, or what they like to call it, the HDAC inhibitors. Okay. The histones assist in DNA packaging and also have a regulatory role. Okay, and if you want to learn about the histones, you should or you have to go back to the introduction and read the introduction again to learn about what histones are and what they do. Okay, so, and as the name implies, histone acetylase is an enzyme that adds acetyl group to the lysine residues of histone tails. So histone is a protein that is consists of different amino acids. Okay, some of them are lysine. Okay, the acetylase will add acetyl groups by a process that we call acetylation to those lysine residues. Okay, what acetylation will do, it neutralizes the positive charge normally associated with the lysine side chain. As you know from your previous classes, some amino acids are positively charged, others are negatively charged, and some of them are hydrophobic or neutral, right? So the acetylation will neutralize the positive charge normally associated with the lysine side chain. Okay, thus it will weaken the ionic interactions between the histones and the negatively charged sugar phosphate backbone of DNA. Because as we said, histones assist in DNA packaging. So histone will wrap up DNA. How histone will interact with DNA? Through the positively charged lysines and the negatively charged sugar phosphate backbone of DNA. If you neutralize the positive charge, that will weaken the interaction. Weakening the interaction will open up that packaging, and that will make space for the for the enzymes to go act on DNA and make proteins or RNA in this case. Okay, histone deacetylase is an enzyme that removes the acetyl group. Well, this is obvious just from looking at the name, you know the effect, but what that will do, if you remove the acetyl group, that means you will keep the lysine positively charged. If you keep them positively charged, then the histone will interact tightly with DNA, and that will prevent the enzymes or the transcription factors from acting on DNA. That will also prevent the repair enzymes from repairing the mutated DNA, which will eventually lead to the growing of cancer. All right. All right. So how about the inhibitors? Several inhibitors are studied against the histone deacetylase or the HDAC. Okay. From those inhibitors, like the romidepsin or the depsipeptide, this circular structure. In this one, the disulfide bond will be reduced to form SH here and SH there. Okay, this will form the zinc binding ligand that will interact with the enzyme, because the histone deacetylase or the HDAC is a zinc metal enzyme, zinc metalloenzyme. Okay, this one was approved in 2009, I think. Well, I'm not exactly sure, but it was approved as treatment against cancer as a combination. The entinostat is a synthetic compound, which is still undergoing clinical trials. Okay, in this compound, the benzamide group, this group acts as the zinc binding group or zinc binding ligand. Okay, The vorinostat, which was approved in 2006, is another HDAC inhibitor. And this one, it uses the hydroxymate group as a zinc binding ligand, just like the one that you saw in the previous part of this lecture that uses the hydroxymate group. Okay, the belinostat, which was approved in 2014, uses also the hydroxymate group, while at the same time panobinostat, which was approved, this one is relatively new, it was approved in 2015, it has also a hydroxymate group. Well, all of these, as you can see, all of these synthetic agents, the entinostat, vorinostat, belinostat, and panobinostat, all of these share a similar design, which is a zinc binding ligand, then a hydrophobic linker, after that a hydrophilic group, then a hydrophobic cap or group. Okay, all of them, zinc binding group, hydrophobic linker, hydrophilic group, and another hydrophobic cap or group. You can see 1, 2, 3, 4. This one is just, if you flip it, you will have this, the zinc, the hydrophobic linker, the hydrophilic group, and the other hydrophobic cap. Why? Because the enzyme has a zinc inside a tunnel, so you need the zinc binding group inside the tunnel. Then you will have the linker, then the hydrophilic group at the opening of the tunnel, and the hydrophobic group as a cap to close the tunnel. All right? Okay. Other enzymes target, well, as you know, cancer is the second killer in the world. Okay. The second killer, it is just second to heart diseases. The heart diseases are considered as the first killer in the world, and the cancer is the second killer. Okay. Of course, we are talking about diseases. We're not talking about other causes of death. All right. So we're not talking about wars or other things. Let's just talk about disease here. And that's why people are studying a lot of targets. They are studying different enzymes to combat cancer or neoplasms. So inhibiting the telomerase enzyme should prevent cells becoming immortal. And there are a lot of active agents against the telomerase enzyme that are being studied or developed, but no one reached the clinic yet. Okay, also inhibition of tyrosine hydroxylase may be useful in shutting down a biosynthetic pathway that is overactive in cancer. Sorry, in cancer. Yep. The TNP 470 is an inhibitor of the methionine or methionine aminopeptidase. And I think you know what do we mean by aminopeptidase and what is the difference between the aminopeptidase and the carboxypeptidase. Okay, I think you know that. And is being studied as an anti-angiogenesis agent, which means the aminopeptidase have something to do with angiogenesis. That's why inhibiting aminopeptide, the methionine aminopeptidase or inhibitors of methionine aminopeptidases will act as anti-angiogenesis agents. Okay, so it is not only enzyme inhibitors that are being studied as anti-neoplastic agents, but also an agonist, like the activation of caspases to induce apoptosis is another possible approach to novel anti-cancer agents. So not only inhibiting the enzymes, but sometimes activating the enzymes will also combat cancer. Okay, and we will talk about the third part later.